So we're going to talk about iterations of integration by parts. It can happen that when you integrate by parts, you get a resulting integral that is better, but it's still not fully integrable. Let me show you what I mean. Consider this integral right here. My first thought, very briefly, is could I substitute?
No.
But clearly no. So I'm going to try parts instead. Identify a good u and a good dv for me.
X squared.
Give me the full sentence.
U equals x squared and v equals dx dx. 2dx dx.
There we go. Okay, good. And so now do the computations.
du equals 2x dx. And v equals yes.
Ah, good. So that we can now appeal to our form. Everybody all together, the integral of u dv.
U dv equals uv minus integral v du.
There we go.
Together. Okay. You were slacky.
We may have to have some togetherness exercises.
Study that.
And here I wrote my u dv a little bit split up just for aesthetic purposes. Okay? Now, what I want to observe is that the integral of v du that I got right here is still not directly integrable.
I can do it again.
But I can do it again. That's exactly right. First, I'm going to do a little bit of cleanup. And now I'm going to observe that I can let u equal
X.
in which case dv is
I can see this.
And this we did yesterday, so we're pretty good at this. We know exactly how this goes.
Oh, x dx minus dx.
Well,
I
now, here's the first thing about doing this the slow way. You see that parenthesis right there?
Yes.
That parenthesis is absolutely necessary and will save your life. Because we are about to do an application of integration by parts, and we're subtracting that integral, which is uv minus integral v du. It has two terms to it. So I need to be very careful with my parentheses that I actually do them. V du. So that when I simplify, I get x squared e to the x minus 2x e to the x plus 2 e to the x plus the obligatory x. And will I check it? Of course I will. So I take my derivative, x first times the derivative of the second, plus the second times the derivative of the first, minus 2 times, once again, first times the derivative of the second, plus the second times the derivative of the first, plus 2 e to the x. And now as I march down through the terms, I can see that these two terms cancel, and these two terms also cancel, and I'm left with the original integral, which works out. Now what strikes me about the slow way of doing this is that there are opportunities for mistakes. And most of those opportunities for mistakes have to do with negative assumptions. Because you can imagine that if I end up having to iterate this twice, or 3 times, or 4 times, and maybe I have an integrand that changes signs on me, and I could end up with triple, quadruple, quintuple negatives. Ugh. We just don't want that. And we don't want it because it is so error-prone. If you take a look at most popular mistakes made by mathematicians, top on the list, above 3 squared equals 6, is making mistakes with a negative signs. Also, 3 cubed equals 9. That's a very popular mistake.
Oh.
Yeah. You can see how that's easy to do. Okay, So, what we would like is to kind of organize this in such a way that we can avoid the negative sign mistakes and so that our work doesn't trip us up. And that is usually done by organizing into a table. The table method is particularly useful when the original u is a polynomial. It can be adapted for other circumstances. But it's generally used when u is a polynomial. And interestingly, the occasions to use parts very often show up when u is a polynomial. So integrals in the form polynomial times e to the x are surprisingly common in practical mathematical work, practical analysis. Okay, so the table method is going to do this. We're going to identify a u and a dv. And we're going to identify the initial u and the dv. Without the dx is going to be understood. Okay? And what we're going to do is to march down on through our process of finding dUs. And we're going to do it successively. So if I take the u here and I make that, and I take the differential to find du, then what I get is 2x dx. And I'm going to go ahead and write the 2x, but not the dx part. And likewise, I'm going to integrate e to the x dx in order to get the v, which is e to the x. So the process of getting from here to here is a derivative process. And the process of getting from here to here is an antiderivative process. And the idea is that we are going to, once we have done one iteration of parts, that iteration of parts is going to generate a term forming. Once we've done that iteration of parts, we're going to iterate again such that the du that I got in the first iteration is now going to become the u that I get in the second iteration, which is what I did here, except for that factor of 2, which I factored out in this guy. But when I organize it in terms of the table, I don't need to. And the next thing that I'm going to recognize is that when I iterate by parts again, that's going to generate another term form. So this term came from our first iteration of parts. This term came from the second iteration of parts with sign changed because I was subtracting. And this third term came from an iteration of parts, but it was the base case, so I was done. It was an integral I could actually handle. And the sign once again changed because I was subtracting the subtraction. Does that make sense? So, each iteration of parts generates one term form. In each case, the du becomes the u for the next iteration. The dv is integrated to get the v for the next iteration. And I alternate signs. Well, we can organize that pretty easily. We can alternate signs by taking alternate signs right here. And we can generate du's by differentiating until I hit 0. And we can generate dv's by anti-differentiating until I get down to here and alternate signs. We are doing examples.
It's a recording thing. But I assume so you can just make.
Yep. Now, how do I generate my terms? Well, it's really easy. Here's the u, and here's the v. And each term for our iteration is generated by u times v. And so here it is. We have u times v is our first term. I usually don't circle them. I usually just go like this. There's my next term. Here's my last term. terms beyond that are all 0. Plus the obligatory constants. So the process then, I took more time explaining and justifying it than I maybe even needed to. The process is, begin with identifying your U and your dV, differentiate down, anti-differentiate up, alternate signs. That's it. This table process is so useful that when I have to do parts, and I frequently have to do parts, if I can look ahead and see I've got to do more than one iteration, I'm going to do it with the table.
Unless it's trig.
What's that?
Unless it's trig, right?
Unless it's trig. Well, right. So the useful thing here is that we eventually get down to 0, right? I can modify this for trig functions, but it's tricky. So let's consider how this would work out with something like this. Before I ever consider parts, I consider substitution. No, not going to happen. So I can look ahead and see that if I do parts, I'm going to end up doing it multiple times, right?
I'll do the table.
Yep. So we're going to set up a table. We're going to start with our positive sign right here. Differentiate on down for me. Go ahead.
3x
Square.
squared. 6x. 6.
Okay. Now, integrate and be careful.
Cosine. 2 cosine.
2 cosine.
Definitely 1/2. Negative cosine of 2x. And once you've done that, differentiate it to check because you know you're better at derivatives than you are antiderivatives, right?
Oh, right. It's
Antiderivative.
Yes, that's right.
We got that.
Okay, keep going.
How do I?
Go.
It's negative sign. And then 1/4. 2x.
That was the most ADD antiderivative I've seen in all the time. Okay, Tife, you're on for the next one.
Positive 1/8.
That's it. And the last one, Jackson.
No.
Negative 1/16 sine 2x.
Check. Take a derivative. Nope.
No, it's positive. Because it's antiderivative.
Oh, okay, there you go. All right, good.
That's one.
15명이라는 거
The derivative of sine is cosine.
One or two or sine.
Here.
Yeah.
Take the derivative of sine 2x, you get 2 cosine 2x. Since we have the negative sign right here, we'll have the negative sign right here. Right?
On the left. The left.
Oh, what's going on here? Yeah, I'm strictly alternating the signs. And I'm strictly alternating the signs because each time I do an iteration, I subtract the integral of b du. And so here's a negative, a double negative, a triple negative, a quadruple negative. All handled for me. Yep. Now we put it together. as UV, U times V. Oops, there we go.
No.
There's our first term.
Negative x cubed x power b. And plus
Plus 3/4 x squared sine 2x
plus
plus 6/8 x cosine 2x minus 6/16 sine 2x. And we're done. So plus C. And there's our antiderivative.
oh yes.
Considering, yeah, the check, but
No,
let's
just kidding, just kidding.
No,
Oh.
not kidding. Let's do the check smart. We know that when we take the derivative of each one of these terms, except for the last one, we're gonna get two terms because of product rule, right? So all we need to do is to check that they cancel. And we can do that mentally. So, first term, first times the derivative of the second, x cubed times the derivative of negative 1/2 cosine 2x would be positive sine 2x over 2 times x cubed, which is our original integral. We're good. Plus 3/2 x squared, minus 3/2 x squared cosine 2x plus 3/2 x squared, 3/2 x squared 2x, and when I take the derivative of sine 2x, I'm going to get 3/2 x squared cosine 2x. These terms cancel. Now, the derivative here, 6x sine 2x. The derivative here, 6 over 4 x sine 2x. The derivative here, negative 6 over 4 sine 2x. The derivative here, 6/8 cosine 2x. Minus 6/8 cosine 2x. And all of our terms cancel and it checks. Yes,
Oh, so for the sign from the,
here,
yeah, so it's always started with the negative.
yes. And you're doing it because each term is the UV from the successive integration by parts, and you're subtracting each one as you go. So it's just accumulating times -1 times -1. This is really -1 to the 0 power, -1 to the 1 power, -1 to the 2 power, etc. Okay. I want to consider a couple of integrals that frequently show up in a technique related to them called solving for the unknown integral. And according to how much time we'll either do one or two examples. I'm going to consider this integral first. It's a product. It's not substitutable. Clearly, we want to use parts. But what do I choose for my u and my dv?
So you choose u as sine x.
Okay.
Then du is x dx dx.
You mean dv?
I also dx.
du
It's
is
dx
cosine
du. Cosine x dx.
Okay.
Dx.
Okay, so we like that. So that gives us then that the integral of e to the x sine x is equal to u times v less the integral of v du. Huh. That's interesting. Can we do it again? We probably could.
You shouldn't be like a trick form, because it would just,
If I choose, what should I choose for my u?
yes.
No,
Wait,
cosine
that,
x.
Which one? Should I choose u equals e to the x, or should I choose u equals cosine x?
because I don't just,
Let's try cosine x. We can come back and consider the other one in just a minute. This one actually is going to turn out to work for me. What's du then? Negative sine x dx. Now, here's where we have to be careful with our negative signs. Of course, this term is here. Now we are subtracting the entire integral, which is
dx cosine x.
less
Minus.
the integral of the du. This is one of those instances of with the triple negatives that I warned you about, right? We've got -1 times -1 times -1. And so I get minus,
dx cosine.
huh. At first, it looks like I have boxed myself
I
into a
know,
never-ending
so-
circle.
So the function is repeating. So you're
Well,
just-
it is repeating, and I could go on for a really long time, except for one lovely fact.
You're like solving for the integral of dx.
Yeah, that's right. The other side of this equal sign is, exactly as Tito said, the integral, oops. You, come back. It is, as Tito said, the integral of e to the x sine x dx. And would you look at that? I have like terms. Ooh. So I can add an integral of e to the x sine x dx to both sides. And when I do, I get this result here.
Oh, I think that means. Oh, I need a cosine. No, different.
So that the obligatory constant c, by the way, pops up because any one of these integrals can generate that c, right? It's in my head, it's still present. So we call this solving for the unknown integral. If I had chosen, I'm going to let you discover this mistake on your own, but if I had chosen
dx.
u to be equal to e to the x and dvb to be equal to cosine x dx, then when I found v, I would get sine x here, and my uv would just be e to the x sine x, and it would cancel out with this. And what I would discover, if you apply parts twice and you swap the u's and the v's, you discover that 0 equals 0, which is a true statement, but it's not helpful at all. Now, the reason I rushed through that, I'd show you, but I want to do a second example of solving for the unknown integral. This is an integral that we're going to see again, and everybody needs to know how to do it. I'll write it in terms of theta. The integral of secant cubed theta d theta.
Is that
Well, I'm going to do something kind of clever.
Wait, why can't we use substitution? Yeah, you. I mean,
Okay, what would you want to substitute?
10.
No.
Ah, what do you? There's a problem. So instead, I'm going to be a little bit clever. What I'm going to do is to let u equal secant theta.
And secant squared theta?
Yeah. Exactly so. So that v is equal to tan theta, and du is equal to tan squared theta. Excuse me, is equal to secant theta tan theta d theta. Now you say, why in the world would you want to do that? But watch. This is equal to the integral of uv, is equal to uv less the integral of v du.
Wow.
Okay. Now, first, this seems like
I think it would be the substitution.
we can be very clever. Let's clean this up a little bit.
Tangent square.
Yep, that's right.
Then we choose secant as mu.
Good. But now we're going to be very clever and recall a thing that we have done previously many times, which is to use trig identities. We can rewrite tan squared as
And
secant
secant
squared
square
by...
minus 1.
Exactly.
No.
And when we do, we get secant cubed theta plus the integral of secant theta. Theta. Now I did several steps here, so check all the algebra. We have the trig identity, we have the addition property for antiderivatives, and we have the distributing of the negative sign. Now, observe. All of this originally is equal to what? The integral of secant cubed.
We have to
Ah, so I've seen this before. I can solve for the unknown integral by adding an integral of secant cubed to both sides.
So 2 secant cubed theta tan theta equals secant theta tan theta plus. Wait, can we just take the integral of secant?
We can.
Natural log of absolute secant theta plus tan theta.
Good. Yes, exactly. All of that over 2
Equals the integral of secant cubed.
equals the integral that we see. We're going to see this integral a couple of times in the future, so you want to practice it. City Board in English class or something like that.
Yeah.
The key insight was first to use parts in the special way that we did. And the second key insight was to pull off the trigonometric ID substitution. So key moves. Are those? Yep, sure can. For the record, cold strong coffee is really disgusting. Well,
Really? It's not just cold coffee. It just tastes different. Like a different.
cold coffee can be okay. Iced coffee, that's nice. But like room temperature, strong coffee. Okay. Questions or comments? I think this is pretty good. Yeah. Do you guys remember doing parts last year?
Yeah.
Not really.
I do.
No. Does it make sense? You remember the formula vaguely, yeah? Does it make sense where it all comes from? What we're going to do next week is we're going to take a look at a second technique called partial fractions. Don't be fooled by the similarity. It has no relationship to parts. And it's actually an algebraic technique that we are going to harness for the purpose of integrating, but it has reach an application that goes beyond just integrals. Partial fractions does. It's a very convenient problem-solving tool, and I find myself using it in various circumstances. We'll also use partial fractions when we evaluate some series, some telescoping series. Okay? Have a great weekend.